Okay, so first of all, we have to have a quick introduction to redox on the basis of. So this we're going to go fast on these topics. Redox on the basis of electrons and oxidation number. So very quickly, let's have a look at redox on the basis of electrons. This is a quick recap on the concepts. Of course, everyone knows redox basically means oxidation and reduction happening at the same time. I'm sure you remember OILRIG. So this is oxidation. Oxidation is loss of electrons and reduction is gain of electron. Now, this is something that you probably already know this, right? So oxidation is loss of electron, reduction is gain of electrons. Okay. Now, based on this, for example, if I have a very simple equations like Fe2 plus 2 electron, plus 1 electron gives Fe3 plus. I'm going to give you a bunch of equations. Very quickly tell me, do you think it's oxidation or do you think it's reduction? Very quickly, please. Could you just mention that in the Zoom chat? Very quickly. Is it just write O for oxidation, R for reduction? Very quickly. Put that in the Zoom chat. So in this equation, as you see, the electrons are being gained. So gaining of electron, that's basically, this is reduction, correct? No, I'm adding one electron, not two electron. That was a mistake. I'm just add one electron there. Sorry, not adding, my mistake. I was thinking something else. Sorry, equation was not correct. Fe3 plus electron gives Fe2 plus. Okay, is it oxidation or reduction? Oxidation or reduction now? I'm going to add one electron to Fe3 plus. That's reduction, correct? Okay. And for example, if it's the other way around, you understand how this goes. For example, if this was copper becoming copper 2 plus 2 electrons, now what is happening? So if you have electrons written on the left hand side, we just say this is the gain of electron. And if you got electron conventionally, if it's on the right of the arrow, that represents the loss of electron. So this is electrons being lost. So we consider this as the copper losing electron. Is that oxidation? Is everyone clear so far? Okay, I'm going to give you an equation. For example, suppose I'm going to give you a redox equation such as zinc plus Cu2 plus forming Zn2 plus 2 copper. Now, very quickly tell me, what do you think is happening here? And what do you think is happening here? Okay, so individually tell me, zinc becoming Zn2 plus, oxidation or reduction? Very quickly, please. O for oxidation, R for reduction. Put that in the Zoom chat. O for oxidation, R for reduction. What do you think? Zinc becoming Zn2 plus, that would be oxidation, correct? Copper 2 plus becoming copper, that's going to be reduction. So that's oxidation and that's reduction. So this obviously is an example of a redox reaction where the oxidation and reduction both are happening at the same time. Now, very important concept. Any substance, this is very good for you, any substance that gets oxidized will act as a reducing agent, and any substance, and vice versa, that means any substance that gets reduced acts as oxidizing agent. Anyone who gets reduced will act as oxidizing agent. Okay, so that's something that you always want to keep a little close watch on this entire lesson. So substance that get oxidized is going to act as a reducing agent. Anyone who gets reduced is going to act as an oxidizing agent. This is very, very important, guys. Of course, unit 5 portions, the lessons are always understandably a bit more intensive, so these concept points are going to play a very, very huge role. Okay, if you're ready, can I just go to the next page? We're just doing some more examples. Just type R for ready in the Zoom chat. Okay. For example, I have one more equation very quickly involving non-metals, because we have to get familiar with both the situations. So if I give you an equation which looks like this, remember this is a quick recap of what is redox on the basis of electron. We just introduction stage at this point of time. So please make sure that you keep commenting in the Zoom chat. Okay, so I'm monitoring the Zoom chat in a different device, just to, okay, don't worry about it. So just keep commenting on your Zoom chat, please. Okay, now very quickly, let's have a look. What happens when chlorine changes to chloride? Could you very quickly tell me, do you think it's oxidation or reduction? Right? O for oxidation, R for reduction. What do you think? Right? O for oxidation and R for reduction, as per whatever you think. So chlorine has become chloride. This is only possible when the electrons are gained. Electrons gained. Okay, just to be on the safe side, you understand 2 electrons have been gained. So what is gaining? RIG. Reduction is gain. So that's basically reduction there. And then obviously what happens when the bromide changes to bromine? So what would be this? So that's 2 electrons lost. So that's oxidation. Okay. So we understand electrons, redox on the basis of electrons. But there is another concept of redox, what you have to know, that is on the basis of oxidation number. So this is redox on the basis of oxidation number. Oxidation number. So you already know how to calculate the oxidation number, but so before we get to that, just a quick recap of what's the definition of oxidation and reduction based on oxidation number. So here's the definition there. So if you look at oxidation, you will find the increase in oxidation number. So increase in oxidation number is called oxidation, and the definition of reduction is basically decrease in oxidation number. Decrease in oxidation number. Okay, so let me give you an example. I'm going to use the same equation so that you understand how to apply this. For example, if I was to give you this equation again, we know zinc is more reactive. Because zinc is more reactive, so that's why it's losing electrons. Okay, so let's do one thing. Let's write down oxidation number of everybody underneath. Now you might remember the rule says oxidation number of any element. Now what is the rule? Oxidation number of any element is always equal to 0. Then there is another rule that you must remember. Oxidation number of monoatomic ions. Monoatomic ions is equal to the charge on the ion. So this is the rule that you have studied probably in your AS level. I'm going to keep going back to those rules just to refresh your memories there. So using these two very quickly, can you tell me the oxidation number of zinc, please, very quickly? What do you think of oxidation number of zinc? Zinc is an element. Because zinc is an element, so the oxidation number will be 0. Correct. This is monoatomic ion. And if it's a monoatomic ion, the oxidation number will be +2. Remember, oxidation number is the residual charge which is built up when the remaining atoms are removed as ions. So we put the charge first and then we put the number. So the oxidation number of zinc when it is in the form of a zinc ion is +2, and this is 0. Okay, very quickly, give me Y for yes and for no. If everyone is okay with oxidation numbers, like how did I get these numbers? Very quickly, please. Are you okay with the oxidation numbers? How did I put them? Y for yes and for no. Everyone, please. Okay, great. Now what you do is you look at the two things which I wrote here. Okay, so oxidation number apparently is increase in oxidation number. So you tell me what happened to zinc. Okay, I'm going to write it this way. So zinc got dash since it's um, okay, now can you fill up all the blanks? You tell me what appropriate words should come there. What happened to zinc and why it happened? Try to fill up the appropriate words, please. Zinc got oxidized or reduced? What do you think? Just write short form. OXI, oxidized. RED, reduced. What do you think happened to zinc? Any suggestions? What happened to zinc? Zinc got oxidized. Since its oxidation number increased from 0 to +2, does that make sense? It's in the middle of my screen. Okay, hold on. Give me a second. Okay, how's it now? Is that okay now? Very quickly, please tell me. Is that okay? Better? Okay. All right, no problem. So everyone is okay? Can we go to our next page? Can we go to our next page? So for example, if this same equation was used in terms of Cl2 plus 2Br minus. Now I want you to write down everyone's oxidation numbers very, very quickly. Okay. We are only using the oxidation number. So what's the oxidation number for chlorine then? What's the oxidation number for chlorine? The oxidation number of chlorine will be 0 because it's element. Element can be in the form of atom or element can be in the form of molecule, correct? And this is an ion. Now remember, when we write the oxidation number, we only look at the charge of the ion. We don't look at the coefficient, okay? So we are not going to look at the coefficient there. Only look at the charge of the ions, and that's -1. And the oxidation number of chlorine when it is in the form of chloride is -1 here, and this is 0. Okay, so now you look at that statement. So Br minus got dash since its oxidation number dash from dash to dash. So we want to fill up that table, please. What do you think happened to the Br minus? What do you think? Do you think the bromide got oxidized or reduced? Could you just write short answers in the Zoom chat? Bromide oxidation number was -1. It became 0, -1 to 0. So -1 to 0, what happened? Is the oxidation number increased, correct? So bromide got oxidized since its oxidation number increased from -1 to 0. Okay, guys, give me yes or no if you're comfortable here so far. Okay, very quickly tell me, what is chlorine acting as? Do you think it's acting as an oxidizing agent or a reducing agent? Very quickly, write down in the Zoom chat. What is chlorine acting as? What is chlorine acting as? You figure it out and write down. Is it acting as an oxidizing agent, which is also called as oxidant, or is it acting as a reducing agent, which is also called reductant? What do you think? So you have to follow this rule. Any substance that gets oxidized acts as a reducing agent. Any substance that gets reduced will act as an oxidizing agent. That's the rule given. So based on that, you tell me, what is chlorine acting as? So chlorine oxidation number from 0 became -1. So this is reduction. So chlorine got reduced. So it's going to act as an oxidizing agent since it got reduced. To see, the thing is, what I'm focusing right now is just the use of the keywords. Just make sure you are absolutely clear as to who got oxidized, who got reduced, who is oxidizing agent, who is reducing agent. And what I'm kind of done with my teaching component here. So what we were trying to understand is, okay, redox can be understood on two bases: one on the basis of electrons and one on the basis of oxidation number. You can use anything. I mean, oxidation number obviously is a bit more easier, but even electrons can be. And then don't forget those star points. Anyone who gets oxidized will act as a reducing agent and vice versa. Is everyone comfortable? Yeah, can we go to our next topic? Our next topic now is actually, there's a couple of equations which I wanted you to become very familiar with, because you will be seeing them very soon. Have a look at this equation. MnO4 plus 8H plus 5 electrons gives Mn2 plus 4H2O. You're going to be seeing this equation a lot, okay? So very quickly, can you figure out the oxidation number of manganese here, please? What's the oxidation number? Can you calculate? Calculate the oxidation number of the manganese. You can write the oxidation number. Very good. You actually might be knowing the name of this particular species as well, but for those of you who need a bit of help, so that's X plus oxygen is -2, and there are 4 of these, so that's -2 times 4 is equal to -1. The sum of all oxidation number of a polyatomic ion is equal to charge of the ion. So that's how we do this, and then you figure this out. So X comes as +7. So you know this as manganate 7 ions. It's very popular in the redox, in the titration. That's purple in color and changes to colorless. And the colorless that you see, okay, so that's purple in color. So these are all very useful information. That's the one which is the colorless solution. So it's going to change into manganese 2 plus. As you see here, so MnO4 negative is changing into Mn2 plus. So the oxidation number here is +7 and the oxidation number here is +2. So what do you think? Is it oxidation or reduction? Of course, you can very clearly see that the electrons are being gained. Electrons are being gained. So you can use the gain or loss of electron to figure this out, right? So what do you think? This is plus 7 becoming plus 2. So the oxidation number decreased. So that's why this is reduction. So again, the use of correct terminology. So you have to say manganate 7 got reduced to manganese 2. That means, so you got to always mention the oxidation number there. So that's reduction. Any questions so far? Is everyone okay? Could you just mention no questions if you have, if you're okay with it? So that's another popular equation which you need to be familiar with. Guys, any questions? So this is MnO4 negative getting reduced to Mn2 plus. It's a reduction equation. So in this case, I'm sure you understand what is MnO4 negative acts. It's acting as, because it is getting reduced, so it acts as a oxidizing agent. So, and you should know that it's one of the powerful oxidizing agent. Okay, we have used this oxidation in alcohols, and so oxidation in alkenes, oxidation of the ethane dioic acid. So it's a very powerful oxidizing agent. Okay. Similarly, there's another example, the Cr2O72 negative. It also acts as oxidizing agent. You have to be familiar with these couple of things. Okay. And it must remember that it gets reduced to Cr3 plus. Okay. So very quickly, can you figure out the oxidation number of chromium here? Cr2O72 negative. Can you write down the oxidation number of chromium very quickly, please? Take chromium as X. So that's basically 2X plus negative 2 times 7. The whole thing is equal to negative 2. Find the value of X. See how much you're getting. Could you mention it? Could you please mention how much you're getting for chromium? 2x minus 14 equals to minus 2. You should be getting x as positive 6. So the oxidation number of chromium is positive 6 here. Okay. So what you see is the Cr2O72 negative when it changes to Cr3 plus. So what you understand is the plus 6. This one is plus 6. So the plus 6 oxidation number is changing to plus 3 oxidation number. So that's reduction. Okay, so this is called dichromate 6 ions. I'm sure you have heard this name. Dichromate 6 ions. You're going to be hearing this a lot in this lesson. So, okay. So I'm done with the introduction of redox. If everyone is ready, let's have a look at what is standard high electrode potential. Is everyone okay with it? Can we go to our next topic? If you could mention why for yes and for no, please. Anybody wants me to go back to any previous page? Okay. So our next topic, what we are doing now, is standard electrode potential. Okay, I'm going to be sharing a particular document in the Zoom chat. Just have a look at it. You're supposed to be having those that document with you. Okay, could you just let me know if you have received that particular PDF file? We will be referring to this page a lot. Have you received it? Could you just confirm? Okay, now what? Okay, first of all, let's have a look at a definition of this. Obviously, the definition has been asked in the exam so many times, so you're supposed to know that. Definition, this is important. Definitions usually worth 2 marks, rarely 3 marks, but definitely 2 marks there. So definition, it is the potential difference produced when I will explain once I finish everything. When a standard half cell is connected to SHE, which is your standard hydrogen electrode, standard hydrogen electrode, under standard conditions. So when we say standard conditions, we are referring to 298K, we are referring to 1.0 mole per dm cube. That's the standard concentration. And we are also referring to the one ATM, which is 100 kilopascal, or you could say 1 ATM, 1 atmospheric pressure. So these are the standard conditions which has to be maintained throughout. So what this definition says, okay, you take a standard hydrogen electrode and you take another half cell. Okay, this is just the introduction of what is called as electrochemical cells. So what I'm saying is you're going to take two half cells. One of the half cell is going to be called standard hydrogen electrode. And then you take the other half cell, which could be like your test electrode. And when you connect them, you get a full electrochemical cell. Okay, so you got a cell, electrochemical cell, which has a cathodic compartment, you have an anodic compartment. Both of them have to be connected by external circuit wires. You also have to have a salt bridge which connects both of them. Okay, and then we'll teach you how to draw the cell. You're supposed to label. A lot of exam questions comes here with drawing and correct labeling of these cells. They will ask you to complete the diagram. They'll ask you to figure out the cell voltage. So a lot of work coming in. Okay, so let's have a look. And all these are pretty straightforward examination stuff as well. Okay, so what I'll do is I will now introduce to you what is called as the standard hydrogen electrode. Once I introduce that and I'll tell you what it is used for, then I will tell you how to figure out the three different situations which will happen. So first of all, what we are doing is standard hydrogen electrode. Now to save some time, I already have some diagrams saved, so I'm just going to quickly copy from there. There you go. Okay, a typical standard hydrogen electrode. So SHE, this basically is our reference half cell. Okay, we're going to compare. This is a half cell. Remember, electrochemical cell is made up of two half cells. So this is a half cell. Okay, so this half cell, a few things that you have to know about it. So the first thing that you have to know is this is our reference half cell. So which means I'm going to compare everybody else with this particular half cell. The second thing is uh, it has the E value which is mentioned as 0.0 V. So that's the equation which you will find in the page which I sent you. Okay, this equation you will find. Now I'm going to talk something very important concept wise. Okay, so please pay attention. I need the concepts to be clear. That is what I'm working. I'm pretty sure you probably might have done this lesson already in your school. So let's have a quick look at the concept very quickly, and please, I insist you do that in the Zoom chat. Could you tell me very quickly, is it oxidation reaction going on or reduction reaction going on? O for oxidation and R for reduction. Could you please mention? What reaction do you think this is? O for oxidation, R for reduction. Everyone has to be convinced because this understanding is very, very important. As you see clearly that electrons are being gained. So either you can very clearly say on the basis of the electrons are being gained. You can also comment on the oxidation number. That is why we started this session by going through what is the change in oxidation number, what is the electron gain and loss concept. So oxidation number of hydrogen in the form of ion is +1, and oxidation number of hydrogen when it is H2 is 0. So +1 to 0 is reduction, or I can say electron has been gained, is reduction reaction going on, correct? Okay, now I want you to focus on another thing. Where is this coming from? Why do I have to agree? Not now. Okay. Sorry. Okay. Could you just look at this page? Okay, everyone look at this page. And do you notice that every reaction mentioned in this page is reduction? Give me Y for yes and for no. What do you think? Isn't every reaction mentioned on this page a reduction reaction? Is that agreed by everyone? Like there is no reaction here in which electrons are being lost. Every one of them is gaining of electrons. Guys, confirmed? I need you to be very, very clear with this. So do you agree that each of this reaction is a reduction reaction? Each of this is a reduction reaction, correct? Okay. What that means now is that all these values that you see, okay, all these values that you see, which we call electrode potential, is actually reduction potential. It's reduction potential, tendency of reduction. How much is the tendency of reduction for sodium ion? Negative 2.71. How much is the reduction tendency of magnesium ion? Negative 2.37. This is reduction tendency, reduction potential. On a scale of 1 to 10, can you tell me, are you clear with what I'm saying? 10 means you are with me. 1, you don't know what's happening. Electrode potential are also called as reduction potentials because these are reduction reactions. This is important concept. I need you to tell me if you're okay here so far on the comment. So this is electrode potential, which is also referred as reduction potential. I'm still waiting for everyone's confirmation that you are with me here. It's important part, please. So all these reactions that you see in your data sheet are reduction tendencies. They are reduction potentials. Okay, all of them. And very, very interestingly, SHE can act as cathode and as anode. It can act as cathode and also as anode. I'm going to give you examples in that situation. Okay, and so why do we need SHE? Okay, first of all, we have a platinum electrode. Why do we need platinum electrode? It's inert. It catalyzes the reaction. So platinum surface, it's inert. It does not interfere in the reaction kinetics. It does help in speeding up the rate of reaction. And I can take any acid. This can come from any strong acid. But be careful. I want an acid who can give me H plus concentration 1 mole per dm cube. So if I take HCl and nitric acid, no problem. But if I take sulfuric acid, I must take 0.5 mole per dm cube because H2SO4 is a dibasic acid. Have you understood? If I take H2SO4, I should take 0.5 mole per dm cube H2SO4 because I need H plus concentration 1 mole per dm cube. So accordingly, I must take any strong acid, not a weak acid, because weak acid, remember, its concentration is not equal to concentration of the H plus aqueous. So I can't take any weak acid. Okay, all done. I must take hydrogen gas at a pressure of 100 kPa. This is the standard pressure. So hydrogen gas is coming from there. These are some bubbles, and that's the reaction which is happening. Okay, now very important concept. At cathode, because we are talking of electrochemical cell, at cathode, electrons are gained. Now these are some concepts that you are studying from before. At cathode, electrons are gained, and at anode, electrons are lost. Okay, now the interesting twist in this discussion is the anode is going to be negative and the cathode is going to be the positive. This is completely opposite of the electrolytic cell that you have studied probably in your IGCSE sessions. This is not electrolytic cell. It's completely opposite of it. Here the cathode happens to be positive. Of course, I will tell you why it's happening. And anode is the one which is negative. But the concept of who's losing electron, who's gaining electron doesn't change. It's still anode losing electron. It's still cathode gaining electron. That is not changing. The, the electrical charge on the electrodes are switched completely. Okay, I will tell you why is it happening in a few moments. Okay, first of all, is everyone okay? Is some stuff about SHE, and there's one more comment about SHE I want to write. So SHE. So what? Why do I need? Why do I need the SHE? So SHE is used to determine. So this is the importance of SHE. Determine the electrode potential. Remember, whenever we write E dot, that's electrode potential of other half cells. That's the job of this, of other half cells. This is the job of SHE. Okay, and that becomes a potential exam scenario as to how would you use SHE to figure out the E dot of this particular half cell or that particular half cell. This is a very popular question that comes in Excel. So you are supposed to know, be able to draw the diagram. You're supposed to be able to write the redox reaction. You should know how to do the cell notation and also the correct labeling, who's losing, who's gaining, who's plus, who's minus. This is a lot of marks there, but easy marks. Okay, they're not tough ones. If you're ready, we'll go to our next page. Any questions at this point of time? If you have any question, if you don't have any questions, could you mention NQ? NQ means no questions. Okay, all okay. So as I said, the actual role of SHE is to help me to figure out the E dot values of other half cells. So what does that mean, other half cells? Now, usually when I teach this particular thing to my students, what I tell them is, okay, look, there are 3 different types of half cells. Get familiar with them. Understand how to draw them. Understand how they look like. Okay. So SHE, of course, doesn't change. It always remains the same. Okay. So let's say I'm going to. Okay, there's a lot of. Fine. So let me do this. Let's say I easy for us to understand this as case one. Understand this as case one. A case one is a metal in a metal ion solution half cell. How is that? Does this make it easy for you to understand which particular half cell I'm talking about? A half cell which is made up of a metal electrode in contact with a metal ion solution. Okay, so tell me if this makes sense to you, that I want to use a zinc and I want to use Zn2 plus aqueous. Give me yes or no if it makes sense to you. Of course, the ion has to be of the same particular element. Does that make sense? Give me yes or no. So I've taken metal and I've taken a solution of zinc ions. And I want to find the E dot of this particular half cell. Remember, this is my half cell. This is a half cell. I want to figure out what is my E dot. Remember what is E dot? We call this electrode potential. And don't forget, electrode potential is also referred as reduction potential. Once again, in case you're wondering, why am I saying a reduction potential? Because the entire data sheet which I shared at you, if you just look at it, it has each equation is actually electrons being gained. Every one of them. Okay. Now, if I look at this page, is there an equation of zinc? Is there any equation where zinc is there and Zn 2 plus is there? Can you tell me what value do you see? Is there any equation that you see where there is zinc atom and zinc ion, and what value do you see? Could you type the value, please? Type the value. I just want to be sure that you are seeing what I want you to have a look at. You saw this equation, equation number 5. I have Zn 2 plus, I have zinc, and the value is negative 0.76. So what I'm trying to do now is I'm trying to make you understand how did that negative 0.76 come? From where it came? How does the chemist know that's the value? Okay, that is what I'm trying to make you understand. Like how we got to know this particular value. Okay, so let's go back here. So the first thing what I need to do is I need to make an SHE. Okay, I can make SHE first or I can use this first, doesn't matter. So I'm making a small SHE of my own. Okay, so just go with it. Standard hydrogen electrode. This particular diagram is easy for you to make in the exams also. There you go. Is that easy? Okay, not much time you will take. So this is I'm trying to make a standard hydrogen electrode here. So okay, this is my SHE here. So from here I'm going to put hydrogen gas at 100 kilopascal. I have here a solution of H plus aqueous. I don't have to mention which acid I took, but I must definitely say the concentration because that's the rule. I must definitely mention the temperature 298 K, so that's done. And always good to mention that this is here a platinum electrode. Okay, so that done. Platinum electrode is done. And this is the SHE, and then I have, this is my half cell number 1. Now I have to draw the other half cell. This half cell is the zinc half cell. Okay, so this is my zinc electrode, correct? Maybe not that big. I need to have a voltmeter. Okay, so now very clearly, this is my zinc electrode. That's the metal. So the solution here has to be Zn2 plus aqueous. The diagram is up to 3-4 marks in the exam with the correct labeling. So please learn it effectively. This is 1 mole per dm cube. You have to mention the concentration and you have to mention the temperature very clearly. Yeah, 298 K. Okay, no, everything done. Now the thing is, this is the voltmeter. So this is what a particular diagram looks like. It still requires some extra information. Okay, let's place a very important component here. This particular electrochemical cell, which is made up of two half cells, one of them is the SHE and the other one is a zinc electrode dipped in a solution of its iron, is not going to work. This cell is not going to work. Tell me what's missing. What do you think is missing? The circuit is not complete. What's missing? Anyone has any idea? So what's missing is what is called as a salt bridge. Have you heard of that? Salt bridge. So when I do this in my class, what I do is I have a solution of copper sulfate and zinc sulfate. I usually use tissue papers, and in the tissue paper I dip the tissue paper in some kind of an inert salt. Okay, so sodium nitrates or potassium nitrate, any inert salt. Okay, so this is called the salt bridge. I'm going to give you a couple of points regarding salt bridge. If this was not there, the cell is not going to work. And this salt bridge is packed with some inert salt, particularly very useful. For example, I could just use potassium nitrate. So I can have potassium nitrate here packed it up inside it. Okay, we'll discuss the importance of salt bridge very soon. This is the complete setup. Now, very important point. Okay, look at these two equations. This is the equation from the data sheet. We don't have to memorize any equation. We're just going to pick up equation from the data sheet. And then if I look at my equation here, I have Zn2 plus 2 electron gives zinc. So I'm just copying from there. We're not memorizing any equations here. So I'm just going to copy the equation from there. It's a reversible sign, fine. I made a reversible sign here as well. It's okay. Okay, done. Then what I'm going to do, I'm also going to pick up the values here. So the value given here is negative 0.76. So I'm just going to write here negative 0.76. That's the E dot values mentioned here. And the E dot value mentioned here is 0.0 V. Okay, now look at this star point very carefully. The more positive, this is like a cheat point, okay? The more positive E dot value is the cathode. Anyone who has a more positive E dot value, who's going to have a more positive E dot value, means more tendency to gain electrons. Somebody who wants electrons very badly will have more positive E dot, correct? Or you can say more tendency to get reduced, more tendency to get reduced because gaining of electron is reduction. Okay, first of all, tell me yes or no. You understand this point which I mentioned here? This is one of the very key points that you can use it throughout this lesson. So this is how you figure out, oh, who's going to be your cathode and who's going to be your anode. Just remember, the one which is showing more positive E dot means it wants the electrons. Now, if you look at the equation, can you tell me out of the SHE and zinc half cell, who's going to act as my cathode? Can you tell me? Who is going to act as my cathode? Who is more positive? This is more positive. Does that make sense? This is a cheat I'm saying. Okay, this is more positive. That means, oh, I think I wrote it wrong. Okay, I'm a bit distracted today. I'm I'm so sorry. It's gone the other way around. Okay. So I have 2H plus 2 electron gives H2. Sorry guys. And I have Zn2 plus 2 electron gives zinc. Sorry. Okay. So that was negative 0.76 V. and that was 0.0 B. Okay, so I understand this is more positive, correct? If this is more positive, is that very clear that SHE is going to act as my cathode, which means this is going to act as my anode? Give me yes or no if everything is okay so far. My apologies, but how come you guys never told me anything? Okay. Is everyone clear as to how do I know SHE is the cathode or anode? Guys, could you very quickly put that in the Zoom chat? I need the Zoom chat to be working fast. Then only we can catch any of these mistakes if that happens during my teaching. Okay, so is everyone clear that SHE is the cathode because it has a more positive E dot? Correct. Now, if you look at my previous page, who is supposed to be losing electron? Who is supposed to be losing electron? Can you mention that? Who is supposed to be losing the electron? Cathode or the anode? Electrons are to be lost at anode, correct? Electrons have to be lost at anode. And anode, that means the flow of electron is going to go this way. Anode to cathode. This is one mark in the exam. They will ask you to mark the electron flow. Did you understand? Electron flow is from anode to cathode. Guys, is everyone comfortable so far? Anyone has any questions? Everyone is okay. It's going from anode to cathode, no problems. Okay. And now can you tell me which electrode is positive and which electrode is negative? Mention that in the Zoom chat. Which electrode do you think is positive and which is negative? I'll open this page once again. According to this concept, cathode has to be positive, anode has to be negative. Correct? So you understand that this anode here is going to be negative. This is negative. The cathode has to be positive. So when you look at the voltmeter, that's negative end and that's the positive end. If you set up the voltmeter correctly, it's going to show the reading. If you flip the voltmeter the other way around, it's not going to work. So anode is the negative charge. Now you're wondering, why is anode negative? Okay, you see how the reaction is going on? Okay, at anode, electron has to be lost, right? Now let's understand how to write this reaction. Can I go to the next page? I will show you exactly what is happening in terms of equations. Okay, so I need to figure out what is the reaction at cathode. So what happens at cathode? At cathode, electrons are gained. Okay, here's one sheet. Copy from data sheet. Whatever equation that you see in the data sheet, you're just supposed to copy it. Okay, so let's go back here. Can you see the equation of the standard hydrogen electrode? Can you see the equation there where the value is 0.00? Please give me yes or no. Equation number 11. Do you see equation number 11? Okay. So I don't have to memorize any equation. I'm just going to copy this equation. Okay. Okay, so they have actually given only 1 mole of H plus. Okay, fine. So no problem. So I'm supposed to just copy that equation. Okay, then I have here electron, and they said we are going to get half H2. Okay, fine. That's the equation at cathode. Now, how do I write reaction at anode? This is one of the very crucial points here. How do I write reaction at anode? I am supposed to write, because at anode electrons are lost. Electrons are lost. So what that means is I'm going to look at that equation. This is the equation happening at the zinc half cell. But in this equation, do you notice zinc ion is gaining electron? So whenever you write the anode equation, please remember you are supposed to flip the reaction from data sheet. Tell me, did you understand why I said this? Flip the reaction from data sheet. What does that mean? Because if you look at this equation in the data sheet, Zn2 plus 2 electrons gives zinc. This is gaining electron. I need to show loss of electron. So do you understand? I need to flip this equation like this. Could you please mention yes or no if you're with me? I have to flip that equation. So literally what I have to do is I'm going to write the anode equation like this now. That was my zinc, equation number 5. Zn2 plus 2 electron gives zinc. Now I'm writing zinc gives Zn2 plus 2 electron. I flip that equation. Okay, I need to add both equations together. First of all, do you understand reaction at cathode, electron being gained is reduction reaction, correct? Isn't that reduction reaction? Electron is gained, and isn't that oxidation reaction? So if I'm going to add both of them, I'm going to get a redox reaction. Does that make sense? Okay, so let me add. But there's one problem though. There's one problem. I got 1 mole of electrons there, 2 mole of electrons there. That's not okay. So how do I fix this? I need to make electrons okay. And then I'm going to add them. So because I have 2 moles of electron there, so I need to multiply this entire equation by 2. Did you understand? And the reason why we did that, because we want to cancel out the electrons there. And when we do that, my final equation becomes 2H plus zinc. That's everything on the what do you say, on the left hand side. And if I multiply this by 2, that's going to become H2, and that remains Zn2 plus. That becomes my redox reaction. On a scale of 0 to 10, tell me, where are you so far? Do you know how to write the redox reaction? Do you understood that anode equation has to be flipped? Did you understand that electrons has to be balanced to cancel them out? Now I have to just discuss one more thing. How did the chemist come to know the value for this equation number 5? How did they come to know it's negative 0.76? Okay, let's have a look. How did they come to know? So basically, anytime you find E cell, which is called as cell voltage, this is sometimes also called as cell EMF. Cell EMF. Okay. So if cell voltage equals to, there is a formula E dot cathode minus E dot anode, which I will tell you is also mentioned as E dot right minus E dot left. So it depends on, it's the same thing. Okay. It's the same thing. Okay. Cathode minus anode, easier way to figure this out. So who's my cathode here? Can you find the cell voltage? Who's my cathode here? My cathode was the SHE. Who was my cathode? My cathode was SHE, correct? What was the value? 0.0. Because I know my value 0.0 because this is a reference half cell. And this one is the unknown half cell. This is the unknown. Remember, this is what I'm trying to find. Now, what do you think the voltmeter is going to give you? Guys, very quickly, please put that in the Zoom chat. What do you think the voltmeter is going to give you? What is the job of a voltmeter there? A voltmeter gives you the cell voltage. Does that make sense? It gives the cell voltage, correct? So what you will see in the lab, that this E cell is already given 0.76 V. Cell voltage can never be negative. Note, cell voltage can never be negative. Okay, so my voltmeter has given me the 0.76. So do you understand now? All I have to do is to figure this value out. So if I ask you to figure this value out, what will you get? Okay, once again, so just to make sure that everyone is very clear. So what's happening? So 0.76 V, this is the cell voltage. This is given by the voltmeter, equals to the E dot 0.0 V, that's the E dot cathode, because I know that's the SHE. So I know that's 0, minus E dot anode. That is what I'm trying to find. This is my unknown half cell. So if I find E dot anode, does that make you understand now how the value came? So that's a 0.0 minus 0.76. So that is why it becomes negative 0.76 V. So this is how the electrode potential of the zinc half cell was actually found out, and that is how it came in the data sheet. On a scale of 0 to 10, tell me how clear you are as to what I said. This is how every one of these values were calculated. Guys, give me a scale of 0 to 1 here, 0 to 10 here. Every one of these values were calculated using this particular style. So the voltmeter gives you the cell voltage, SHE is the 0, and you just have to figure out the value of the other half cell. That's all you have to do. Is everyone clear so far? Still waiting for response in Zoom chat. So this is one example of case 1. I do the maximum talking in case 1, first example. Now my talking is going to be reduced. So I'm going to give you another situation very quickly on case 1, and then we'll keep moving from there. Remember, case 1 is a metal in contact with a metal solution. So now you know how to draw the diagram, you know how to do the labeling. Electron flow goes from anode to cathode. You know anode is negative, cathode is positive. And then remember how to figure out who's the cathode. The one which has more positive E dot is the cathode. And then how do we do the redox reaction? So we write cathode equation directly as it is from the data sheet. But for the anode, remember to flip the equation from the data sheet. Just reverse the whole thing. And then you make sure the electrons are balanced out, do the appropriate multiplication, cancel the electrons out, and then you get the overall redox reaction of this. Now there's one thing left before I give you another example. This is called cell notation. Have you heard of cell notations? There are examination questions I have seen in your exam papers where you are expected to know cell notation. They might give you MCQs with cell notations, and they will ask you. Cell notation is called cell representation. Okay. Cell notation. Basically, it's a cell representation. So cell notation, it starts off from the anode. So who's your anode now? Who's your anode? Zinc is the anode. So it starts with the anode, and this zinc is changing into Zn2 plus. You basically look at your redox reaction there. Your zinc is changing into Zn2 plus. Okay, so this is your anode. Don't forget, the electrons have been lost. So when you write this, don't forget to put that. Don't forget to put the concentration 1.0 mole per dm cube, 298 K. You need to put all that. And then the double line here is the salt bridge. This is the salt bridge. And then you write the cathodic side of that. Now in cathode, see, at anode electrons are lost, so zinc is losing the electron. So who's gaining the electron here? So the H plus is gaining the electron. So what you can do is you can look at the redox and say, okay, so I have my 2H plus aqueous, and that's changing into H2 gas. You can put the state symbols there, looks very nice. And then you don't forget, once again, 1.0 mole per dm cube. Write everything, because you never know what all they want. And that's it. This is called cell notation. Is everyone clear with cell notation? Is everyone okay with cell notation? So now you know how to do cell notation, you know how to do redox reaction, you know how to draw, how to label, how to find cell voltage, everything, correct? Okay, that is why sometimes you may even find this in your books: E dot cell equals to E dot right minus E dot left. So who is on your right? Who's on your right? You have, if you look at the cell notation, on your right is your cathode and on your left is your anode. If you look at the cell notation there. Okay, so if you have any questions, I'm waiting. I'm going to give you more examples now to work. That's it. My teaching component is kind of done here. So first of all, tell me if you have any questions for me. Please mention that in the Zoom chat if you have any questions. No questions? Okay, so I'm going to give you some examples to work on. We are still discussing case 1. So I gave you case 1 where I gave you zinc half cell. So zinc half cell basically is zinc electrode dipped in a solution of its ion connected to an SHE. Okay, so I'm going to give you now another half cell. Okay, let me see if I can just copy this as it is. Save some time. Okay. I'm giving you another situation. I'm just trying to save some time here. So I have a very similar diagram. Okay, and this time I'm using copper electrode. So what I've done is, this is another example. Another example of a metal in contact with its ions in solution. So it's still case 1. It's still case 1 example. But this time the metal which I have used is copper. So if you look at your data sheet, please look at equation number 13. If you look at equation number 13, copper 2 plus, no, equation number 14. Copper 2 plus gaining 2 electron gives copper. We are not doing equation 13, we are looking at equation 14. Copper 2 plus gaining 2 electron gives copper 0.34. Okay, let's have a look at that. So I'm copying this equation, Cu2 plus 2 electrons gives Cu. The E dot value which has been mentioned is a positive 0.34. We are trying to understand, okay, how did this come about very quickly. Okay, so how did the chemist come to know it's 0.34? First of all, how do the chemist comes to know who's cathode, who is anode? In actual scenario, you will actually have a voltmeter in your lab, and if your voltmeter is not correctly connected, obviously you will not see any readings. So that is one way for you to figure out who's cathode, who's anode. If your voltmeter is correct, you will see deflection, and the voltmeter clearly has plus minus charge written on it, so you know who's positive, who's negative straight away. Okay, but since we don't have a voltmeter, so I gave you a cheat. I said, okay, fine, the one which is more positive, look at my star point here, uh, the more positive E dot is going to act as cathode. The one who has a greater tendency to gain the electron, greater tendency to get reduced, will act as cathode. So if I look at these two, clearly I find that this is more positive. because if this is more positive, which means I hope everyone is very clear. Now this is going to act as cathode and SHE is going to act as anode. So that is what I was trying to say, that the SHE can act as anode also and it can act as cathode also. So in this question you see SHE is now acting as anode. Okay, so what about the electron flow? Now if you look at my previous point, electron flow is from anode to cathode. Electron flow is from anode to cathode. That is the rule, because anode is the place where electrons are lost. Correct? So which means the electron flow is going to be like this now. Okay, that's a mark for you. And then so SHE is my anode, that is my cathode, right? So first of all, let's write down the redox reaction. So what is the cathode equation? What did I say? Cathode equation, copy from the data sheet. So cathode equation, my copper is the cathode, and don't forget cathode is my positive terminal, anode is my negative terminal. So this is the negative and this is positive. Okay, so cathode is positive here. So what equation reaction happens at cathode? I'm just going to copy it from the data sheet. So this is the equation. Cu2 plus picks up the 2 electron and changes to copper. Okay, done. What about the anode? Anode is negative here. And don't forget I used the word flip the reaction. Don't forget electrons lost. Correct. So this is the anode equation reaction there, right? 2H plus gaining. So this equation is now going to be acting as an anode, SHE equation. But the problem is this equation, electrons are being gained. So I have to flip this equation. This equation goes this way. This equation, this equation goes this way. This is going this way. This is going this way. So I need to flip these equations. Okay, so when I flip this equation, now what happens? I have H2 giving 2H plus 2 electrons. Okay, so now I'm going to add them up, and that's basically how I get my redox reaction. So how do I get my redox? My electrons are cancelled out. So you can cancel the electron from the left, the electrons on the right, you cancel them out. And then your overall equation becomes Cu2 plus H2 gives Cu plus 2H plus. So that becomes the overall redox reaction there. Okay, so how did the chemist come to know it's positive 0.34? Remember, the formula says E dot cell, as per your books, it says, okay, let's do the cell notation. Okay, let's do cell notation first. Cell notation. Would you try to do this yourself? Can you work out the cell notation? You're supposed to write the anode first and then the cathode. So who's your anode? So if you just look at the equation, you can figure this out. Your anode is your SHE. Look at the equation of the anode. Hydrogen is becoming 2H plus. So what you do is you just write H2 gas, and it's changing into 2H plus aqueous. But the moment you write ion, don't forget the concentration, 1 mole per dm cube, and don't forget the temperature, 298 K. Remember, this bit is the anode bit. And then you do this double line, that's the salt bridge. And then you mention the cathode bit. Now cathode, electrons are gained. So who's gaining the electron? You just look at your equations. Your copper 2 plus is gaining electron and changing into copper. So who's changing to who? So you just mention that. So copper 2 plus, but because you're mentioning ion, so you got to say again 1 mole per dm cube, 298 K. That is changing into copper. Might as well put solid there. Okay, good. All state symbols done. That is your cell notation. Everyone is clear of cell notation? Everyone is clear of cell notation. Okay. Now, if you look at the formula, it's E dot cell equals to E dot right minus E dot left. You can do that. Or you could do E dot cathode minus E dot anode. It's always cathode minus anode. Okay, so who is going to give you the cell voltage? So cell voltage comes from voltmeter. Don't forget, this is coming from voltmeter. So your voltmeter is going to tell you 0.34 V. That's the cell voltage. Okay, and who's your SHE now? SHE is acting as anode. Because SHE is my anode, correct? So I know this is my unknown half cell, and that is 0.0 V. Because this is SHE. Are you guys following me? Because SHE is 0, and all I have to do now is to figure this value out. Okay, so when I figure this value out, so I get E dot cathode equals to positive 0.34 V, and that is how this value got pasted in the data sheet. I'm just trying to explain you how each of those values came. Okay, so I'm done with case 1, and I'm waiting for you to have any questions for me. How to draw, how to figure out who is cathode, who is anode. These are the important stuff here. How to mark the electron flow. Still waiting for any questions if you have. If you have no questions, could you please type NQ? NQ means no questions. I will quickly talk about the functions of salt bridge. I'm going to give you a small note what you should be knowing as to why do we need the salt bridge. Okay, so I think I already kept that ready for you. I will strongly advise you that you should learn this, because this is an easy possible potential question as to what is the importance of salt bridge. So just to save some time, I just mentioned everything here. I hope that's okay with you. So salt bridge, could you just quickly read through? So salt bridge is completing the circuit by joining both the electrolytes. It helps to balance the charge as the electrons flow, because it keeps the electrolytes neutral. It neutralizes any charge built up in the solutions. This is also a question which I have seen in the exam, why a metal wire should not be used. I've seen this question there, because a metal wire cannot be, it's not a good thing for us to be acting as a salt bridge, because you need the ions to move, and the metal wire only allows the electrons to move. It doesn't allow the ions to move. Okay, so that's the reason why metal wire should not be allowed. A couple of examples of what are the chemicals which could be used in salt bridge. Usually potassium nitrate, potassium chloride. They are inert, they don't interfere. That's usually the idea. Okay, okay, still waiting for any questions from you. So I'm done with case 1. Case 1 is when a metal is in contact with its solution. So all you have to do is learn the diagram of case 1. Of course, you have to learn the diagram of the SHE. That definitely has to happen. So let's have a look at case 2. When I say case 2, this is the second type of half cell. There are 3 types of half cell you have to learn. SHE you have to learn separately. Apart from the SHE, there are 3 different types of half cell. SHE is a very special half cell that is used to figure out the EDOT of everybody else, other half cells. Okay, so let's have a look at case 2.
Hello? Sure.
Yes, hi.
Yes, sir. Can you please go back to the salt bridge
Sure,
part
sure,
for
sure.
just 2 minutes?
This one? I'm going to be sending the PDF of this after the class.
Okay, I'm done. It's okay.
Done? Okay, yeah, sure. So case 2. Now, how is case 2 different from case 1? Because in the exam, they will not tell you it is case 1, case 2, case 3. You have to figure out, oh, does this belong to case 1? Does it belong to case 2? Accordingly, then you have to figure out the diagram and the labeling and everything. Case 2 is a situation where your half cell is a non-metal. A non-metal in contact with its ions in solution. A non-metal, which means if you look at the diagram of case 1, when I gave you zinc and when I give you copper, okay, you see that that was a metal electrode and it was dipped in a solution containing its ion. That's what a case 1 half cell looks like. Of course, SHE looks like this. That there's not going to be change in the SHE. But that's what a case 1 looks like. But the question now is, what do I do to draw a case 2? Well, case 2 is a non-metal. Obviously, we are going to deal with gases here. Okay, so easy way for you to remember, it's kind of exactly how an SHE looks. So think of this as you're drawing two SHEs. Okay, so let's have a look. Of course, I need to, for example, okay, for example, my I need a chlorine gas in contact with chloride ion, 1.0 mole per dm cube, 298 K. As you notice here, this is my half cell. This is my unknown, well, not unknown really, but this is a half cell whose E dot I have to find. This is the half cell, okay? And I want to figure out the electrode potential. Don't forget, this is called electrode potential, okay, of this half cell. That is my intention. So of course, when I look at my data sheet, okay, do I see an equation where there is chlorine and Cl minus? Let's have a look. Do we have an equation with chlorine and Cl minus? Sure, there should be. Yep, there is. If you look at equation number 29, okay, I'll make it more bigger. So equation number 29, if you have a look, that is Cl2 plus 2 electron gives 2 Cl minus, and there is a value given 1.36. Okay, so we already know uh, how does that work. Okay, so let's have a look. So I need to figure out how does this half cell look like. Every equation, here's something interesting for you. Every equation, this 31 equations that you see, every one of them is a half cell. This is 31 half cells they have given. Okay, every one of them can be drawn. Okay, so how to draw this particular half cell? So what you do is, first of all, you just figure out the SHE. So I'm just drawing the SHE very quickly. Okay, so that is my SHE. I'm going to use this as my SHE. Okay, so which means I have to put hydrogen gas here at 100 kPa. I know that's the platinum electrode. Don't forget all the labelings. Then I know this is a solution consisting of H plus aqueous, whose concentration is 1.0 mole per dm cube. And since it is a solution of standard conditions, I have to mention my 298K. Okay. Now this is my unknown half cell is happens to be a chlorine gas, which means I have to draw exactly like this. There is no difference here. Okay, so think of this as you're making another SHE, and for the sake of convenience, I'm putting this nozzle this side because I need to put chlorine gas from there. So think of this like you're reversing it. You get my point? Think of this that you're reversing. There you go. Guys, do let me know if a prayer break would be required. And then there you go. You see what I did? So now everything remains the same, but this time I'm going to put here chlorine gas, and that has to be 100 kilopascal or 180 m, whichever you prefer. And then this is again platinum electrode, because you cannot have an electrode made of chlorine. That doesn't make sense, right? So you still need platinum electrode. But the solution must contain, look at the equation, the solution must contain the chloride ions. So I can take any solution who can give me 1 mole per dm cube chloride ion. I don't care from where the chloride ion comes from. So I need 1.0 mole per dm cube. That should be the concentration of the chloride ion. And I must maintain temperature at 298 K. So I'm going to join these two external circuit wires. Then I'm going to put a voltmeter there and I'm done. But don't forget, this thing is not going to work till I don't connect a salt bridge. So I need a salt bridge. Don't forget, without that, this is not going to work. So I'm going to connect this with a salt bridge. So that's done. Okay, so that's my salt bridge, and as we just said, salt bridge is usually packed with potassium nitrate or potassium chloride or something. Remember, these are the two highly recommended. They don't interfere. Their salt bridge is used to maintain electrical neutrality. It completes the circuit by joining both the electrolytes. That's the function there. Okay, and this is like made up of a semi-permeable some material which is used to allows the ions to move. That's the most important thing. It must allow the ions to move. And that's my voltmeter there. Okay, so let me just write down the equation from the data sheet. I don't have to memorize any equation. All I have to do is look at that equation. The chlorine equation is Cl2 plus 2 electron gives me that 1.36. So I'm just going to copy that. Cl2 plus 2 electron gives me 2Cl minus, and the E dot mentioned is a positive 1.36B. Okay, done. And for the SHE, once again, I don't have to memorize the equation. It's already given here somewhere. And that's H plus. They already gave only 1 mole, so just we'll stick with that. So H plus plus 1 electron gives half H2, and this is our reference whose value is this already mentioned. Okay, now I gave you some cheats before. Can you tell me who is cathode? Who is cathode? The chlorine half cell. So this is called as chlorine half cell. Usually we call this chlorine half cell. Do you think chlorine half cell is the cathode, or do you think the SHE is cathode? Can you very quickly tell me? So this is more positive. It's very easy now, correct? This is more positive. So I know this guy is going to act as my cathode. And don't forget, if this is the cathode, that's the one going to be positive, which means my SHE is going to be the negative here. And then they will say, okay, mark the electron flow. Don't forget, the electron always goes from anode to cathode. So the electron flow is going to go this way. It's going to be anode to cathode. And why is it going from anode to cathode? Because at anode, electrons are being lost. Right. Then how do we write the equation? So let's write the cathode equation. Cathode equation, I'm just going to copy as it is from the data sheet, which is Cl2 plus 2 electron gives 2 Cl minus. Okay. What about my anode equation? Okay, so don't forget cathode is positive, anode is negative. What about my anode? Remember, I need to flip the anode equation. I need to flip it this way. Flip the reaction, correct? That's the hint I gave you. Why? Because anode electrons are lost. So I'm supposed to write like this, correct? I'm supposed to write like this, right? No. Yep. Okay. Is that okay? Yep. Then I'm supposed to add these two equations together to get my overall redox, and by this time you know how to do it. So I need to multiply this equation by 2 because I need to make the electrons equal. So I need to cancel out the electrons. And when I do that, my final equation becomes Cl2. And then when I multiply this by 2, it becomes like H2. And then that is 2Cl minus from the top equation. And the bottom equation becomes 2H plus. So that becomes my overall redox reaction. And then how did the chemist come to know the value? So this was the formula. Okay, let's do the cell notation. I keep forgetting it. Can you figure out the cell notation? This is a skill that I want every one of you to be very good with. Cell notation. How do we do cell notation? You write the anode first. You write the anode first, and then you write the cathode. Don't forget, that's the format. So who's my anode? So my, of course, you can look at the redox reaction and you can do that. So my hydrogen, which is gas, changed to 2H plus aqueous. So this is, you could mention extra data. Do not be afraid of this is 100 kPa. Mention that data. I should have mentioned previous also. 1.0 mole per dm cube, 298 K. Done. Salt bridge, don't forget. And then who's my cathode? Who gained the electron? My Cl2 gas, which was at 100 kPa, gained the electrons to become 2Cl minus aqueous, 1.0 mole per dm cube, 298 K. Waiting for any questions, or if you want to, please be comfortable to use the mic and ask me. That's the cell notation there. Is everyone clear? Any questions? There should be 2Cl minus. Should the 2Cl minus not be before Cl2 in the cell notation? Oh, my cell notation is not correct. Thank you very much. Who lost the electron? No, it's the other way around. Thank you. This is how I test who is. Thank you. 2Cl minus becoming Cl2 gas. Sorry, it's the other way around. That's the one who's losing the electron, right? Oh, wait, hold on.
Sir, how did
No,
hydrogen
no, 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 no,
gain
no.
electrons and
I
become
know,
H
I know,
plus?
I know, I know. Okay, say that again. So who lost the electron? We messed up something, right? Who's the cathode here? Cathode was the chlorine. Is
Sir, the hydrogen lost electrons.
the hydrogen lost the electron, correct? So that means, yeah. So this is correct, yeah, correct. Just keep checking my work. And then who gained the electron? So we were correct. What was the mistake in it? Was something mistake? Chlorine gained the electron and changed to 2Cl minus. Wasn't this right? Abdullah? Because who gained the electron? Chlorine gained the electron, correct? You're okay? Just give me yes or no. Yeah, yeah, it's correct actually. So hydrogen lost the electron to become H plus, correct? So and the chlorine gained the electron to become Cl minus. We're right. Chlorine became Cl minus and H2 became. So we can just look at the redox reaction and figure this out. Okay? I think, yeah, we were right. So that is 100 kPa, and then that is 1.0 mole per cube, 298 K, 100 kPa. I can give you an extra question for homework. I mean, just practice this when you have time. You just have to learn how to draw the diagram, how to do the labeling, mark the electron flow, get the overall redox reaction done. Is everything okay, Baba? The see the thing is when I get the redox reaction, the question is like why do we have to multiply the equation by 2? Why do we do that? Think of this as simultaneous equation. Okay, so when I want to cancel it, I don't want to see electrons in my redox reaction. To cancel, so I need to cancel out all the electrons. To cancel the electrons, I need to multiply the anode by 2. Does that make sense? The idea is that we should not see electrons in the redox reaction. Okay, so I need to cancel out every electron that is possible, and in order to do it appropriately, whatever coefficients I need to use that to multiply the anode and cathode equation accordingly. For example, if somebody had 3 electron and the other equation had 4 electron, so you multiply by 4 and 3 and you cancel them out. Okay, done. So I can give you like a homework, but I want to introduce case 3 also with you before I finish the class, if that's okay. So maybe you can try this. as a case 2 scenario. Okay, so I want you to a cell made of, so I want you to try this. Okay, you draw the SHE as usual. Your cell, remember, must contain two half cell. So this is half cell number 1, and I want oxygen half cell in acid medium. Oxygen half cell in acid medium, because oxygen also is non-metal. Okay, so this is like a homework question for you. Okay, please have a go at it when you can, for extra practice. Okay, can you just tell me which of equation can you actually select for oxygen half cell in acid medium? There's a reason why I gave that equation. Let me just check. Do you think you can use equation number 16? Give me yes or no for equation number 16. I can't, because there is, when I say acid medium, I need to look at, okay, can you tell me which equation do you think will work from this list which I've shown? Can you tell me which equation number? No, we don't take equation number 20. We don't work with hydrogen peroxide. Okay, so just dump that equation. Is there any other equation given? Okay, have a look at equation 27. No, we don't work with H2O2, guys. Okay, that's hydrogen peroxide. We don't do that. Look at equation number 27. Yes, when I say oxygen half cell acid medium, that's the one, because O2 plus 4H plus, that's the acid medium there. That's coming from the acid, which is 1.23. Did you get it? Okay, so I'm just going to write that equation just for reference. Okay, so this is O2 plus 4H plus 4 electron. Okay, and what was the value? 1.23. Okay, so that gives 2H2O, and the E dot value is 1.23. Can you tell me in the diagram which gas is going to come from the nozzle? You understand? You will put oxygen gas here. Okay, tell me what will be the electrolyte. What will be the electrolyte? Look at the equation and tell me. Don't put O2 minus. There is no O2 minus here. Don't think, oh, this is Cl2 and Cl minus. No. So I should put, if I put O2, I should put O2 minus. No, there is no O2 minus in this equation. You see there is H plus here. Do you see that? Correct? H plus. So when you draw this diagram, it is going to look like this. Only difference is oxygen gas will come from here, and in your electrolyte there will be H plus aqueous 1 mole per dm cube. Can you please confirm that you have understood that? In your electrolyte you will mention H plus aqueous. You will not mention O2 minus. There is no O2 minus. Guys, give me yes or no if you are clear. Do not mention O2 minus here. Here you will mention H plus aqueous. Okay, so everything remains exactly the same. Do you want me to quickly do that, or you can handle it? You will copy everything exactly the same, but only O. Do you want me to do it very quickly, just to be on the safe side? It won't take much time. I'll just quickly copy, because this is not homework anymore. Because this is very easily misunderstood, the whole thing. Now, just what I'm saying is, okay, this is all gone. Okay, let's figure this out very quickly. Very quickly. Let's not take much time. There you go. Oops. Okay, so this is not chlorine gas anymore. That's going to be O2 gas. Okay, and then the only thing what I'm saying is that is not Cl minus anymore. It is H plus aqueous. Guys, give me yes or no if you're okay with it. And that equation is gone. And then you just mention that equation here. That's O2 plus 4H plus 4 electron gives 2H2O, and the E dot mentioned is a positive 1.23, which means that is more positive. Everything remains the same. This is more positive, so that is the cathode here as usual. Any questions? This is your cathode, which is going to be positive, and the electron flow, this is my anode, which is going to be negative. Electron flow is from anode to cathode. Okay, since we were talking about the balancing, very quickly, this is to clear some doubts. Yahya had put a question. Yahya, did you get the answer to that question? So the cathode was the O2 plus 4H plus 4 electrons. Okay, can you tell me how do I fix this equation? Because at anode I have this equation going on. Okay, I need to flip the anode equation. So my anode equation is going to be like half H2, giving me H plus electron. Guys, how do I fix this? Please suggest, particularly someone who had a doubt in the previous question. How do I fix this? I need to multiply this equation by 4. You get the idea? So the idea is I want to get rid of all my electrons there. I don't want my electrons there. So all the electrons are gone. Okay, got it? Okay, so that is O2 plus 4H plus half times 4. That's going to be 2H2, correct? Please check. Plus 4H plus. Please check. Is this the overall redox? Give me yes or no if everything is okay. Yep, okay, good. Are you sure? Okay. Can you help me with the cell notation then? Okay, start with the anode. Cell notation. Start with the anode. So who lost the electron? Hydrogen lost the electron, correct? So hydrogen lost the electron. Okay, so I can also say I can use my overall redox. So I see there are 2 moles of hydrogen and I got 4 moles of H plus. Did you understand what happened here? Guys, I need you to confirm. I'm using my overall redox reaction to get these coefficients. Is that okay? Yes, can we cancel the H plus? We can cancel out the H plus. Why not? We can cancel even this one out. Yeah. So what's the final overall redox reaction then? So that's O2 plus 2H2 gives 2H2O is the final overall redox. Yeah. Anything that is on the left and right can be cancelled out. Yep, you're right. So that's the final redox. Okay, so that's done. Okay, but cell notation, I have to show everything correctly the way it is. So how do I do that? And who's my cathodic compartment? Who's gaining electrons? So I have my oxygen half cell gaining electron, right? Cell notations, I have to show everything what's going on. So I have oxygen gas and it's 100 kPa. It is in acid medium, so I need to show what is happening as per the equation. Okay, so see, if it is this acid medium, just a representation, you are allowed not to show the coefficients also. There's no problem. Okay, so I'm just showing you with the coefficients in acid medium and it's changing into H2O liquid. So you're literally copying the equation without the electron. So that's the anode, that's the cathode. You're allowed not to mention the coefficients as well, which means I can just write this way in a simplified way. Also allowed is this H2 gas slash H plus aqueous. At least you have to put here 2. Now I think we can stick to the coefficient. I need to confirm whether it's allowed without the coefficient. Let's work with the one with the coefficients as per the redox reaction there. The reaction at anode and cathode. Is that okay with the cell notation? I just put all the data as per the cathode and anode equation what we wrote. Is the cell notation okay? Anode H2 lost the electron to form the H plus. At the cathode, the oxygen half cell, that's the one who's gaining the electrons and changing into H2O. Guys, yes or no if everything is okay?